Welcome to the Explainer. All right, today we're going to dive deep into the science of the very small, a world that is not only bizarre, but is literally the foundation of our reality. We're talking about quantum physics, which is, hands down, the most successful and mind-bending scientific theory of all time.
All right, let's jump right in, but maybe with a little friendly warning first. The folks over at Nova really said it best. The quantum realm, it just doesn't play by the rules we're all used to. It's famous for being deeply confusing, even for the physicists who live and breathe this stuff every day. So yeah, buckle up.
You know, for centuries, we pretty much thought of the universe as this giant, predictable machine, kind of like a clock. If you just knew where all the gears started, you could predict exactly where they'd end up. Well, quantum mechanics comes along and just shatters that entire idea. It tells us that, at its core, reality isn't about certainty at all. It's about probability. It's a game of chance.
And that brings us to our first really weird idea, superposition. Think about a spinning coin, right? Before it lands, is it heads or tails? Well, in a way, it's kind of both possibilities at once. Superposition is the quantum version of that, only it's way, way stranger. An electron, for instance, isn't in one specific location. It exists as a cloud of probabilities, a combination of all the places it could possibly be, all at the same time.
So, what does that actually mean? Is the electron everywhere or nowhere? These questions you see here, they're the exact same questions physicists have been wrestling with for a century. The wild thing is, the math works perfectly. It makes predictions with mind-boggling accuracy. But the theory itself doesn't actually give us a simple, common-sense answer for what's going on before we look. And that's one of the great mysteries. Okay, so if you thought superposition was weird, get ready for entanglement. Picture this. You have two special coins. You keep one, and you give the other to a friend who travels clear across the galaxy. Then you both flip your coins at the exact same moment. If yours lands on heads, you instantly know, with 100% certainty, that your friend's also landed on heads. Every single time. That's entanglement. Particles linked together in a way that just ignores distance.
You know, even the great Albert Einstein himself was really bothered by this. He famously called it spooky action at a distance, because it seemed like information was traveling faster than the speed of light, which should be impossible. But here's the kicker. Experiment after experiment has proven this spooky connection is absolutely real. It's just a fact of our universe, as bizarre as it sounds.
So what this all boils down to is this huge split, right? On one side, you've got the classical world we see and touch every day. Things are solid, they have definite properties, and their actions are predictable. But underneath all of that is the quantum world, a world of pure potential, probabilities, and these strange, spooky connections.
But here's the crazy part. For all its weirdness, quantum mechanics isn't some dusty old theory just for blackboards. It is, without a doubt, the most successful theory we've ever come up with. The transistors in your phone? That's quantum. The laser at the grocery store checkout? Quantum. The atomic clocks that make your GPS work? Yep, you guessed it, all powered by quantum mechanics.
And there's no better example of this than the LIGO observatory. It's incredible. They use these ultra-stable, quantum-powered lasers to hunt for gravitational waves, actual ripples in space-time caused by things like black holes colliding. Basically, they split a laser beam in two, send each half down a really long arm, bounce them off mirrors, and bring them back together. Usually, the two beams cancel each other out completely. But if a gravitational wave passes by, it stretches one arm and squeezes the other just a tiny, tiny bit. The beams don't line up anymore, and bingo, you get a signal. We're using quantum weirdness to see the universe shake.
Okay, let's switch gears a bit and talk about computing, because this is where things get really interesting. All of our technology right now, from your smartwatch to the biggest supercomputers on Earth, is built on one simple idea, the classical bit. The best way to think of it is just as a light switch. It can be on or it can be off. That's it. Two states.
And we just label those two states 0 and 1. It doesn't really matter what it is physically. The voltage, a tiny pit on a Blu-ray disc, whatever. At the end of the day, it's always an either-or choice. And that simple language, just zeros and ones, is the foundation of literally everything digital.
But this is where quantum mechanics just blows the doors off everything. Quantum computing doesn't use a bit. It uses a qubit. And while a normal bit has to choose, it's either a 0 or a 1, a qubit, thanks to superposition, can be a 0, a 1, and a whole spectrum of possibilities in between, all at the same time.
Here's a great way to think about it. A regular bit is like that light switch, right? Two positions, on or off. A qubit is more like a globe. You can say the North Pole is 1 and the South Pole is 0, but the qubit's actual state can be any point on the entire surface of that globe. That ability to exist in that rich mixture of states is what gives it this incredible power to hold so much more information.
Okay, so why should we care? What's the big deal about these superpowered qubits? I mean, what can we actually do with them that we can't already do with the computers we have now? What kind of new power does this really unlock?
Well, the answer is a huge deal and has massive consequences for pretty much everything we do online, from banking to national security. The most famous and maybe most concerning application is its ability to break the very encryption that keeps all of our digital information safe right now.
See, the way most modern encryption works is based on a really clever mathematical trick. It's super easy to take two massive prime numbers and multiply them together. But if I give you that resulting giant number and ask you to find the two original primes, well, for a normal computer, that's practically impossible. It would take billions of years. That problem is the lock on our digital data. A quantum computer running a specific program called Shor's algorithm could theoretically pick that lock like it's nothing, shattering the foundation of modern digital security.
Now, let's be real for a second. We're not there yet. Not even close, actually. Today's quantum computers are pretty small, and they're really sensitive to errors. Building a big, stable one is one of the toughest engineering challenges on the planet. But the potential applications? Wow. They go way beyond just breaking codes. We're talking about things like simulating molecules perfectly to discover new medicines, designing revolutionary new materials from the ground up, or optimizing incredibly complex systems like a whole country's power grid. These are problems that are just too big for any normal computer to ever solve.
And all of this leaves us with one final, kind of mind-bending thought. For 100 years, quantum theory has completely reshaped how we understand reality itself. Now we are starting to build machines that don't just use its effects, but actually think in its native language. So the question is, what happens when our technology finally learns to play by the universe's true rules?